So I want to talk about the Archimedean property a little bit. This is the if-then statement. It says if a and b are positive integers, so positive whole numbers, 1, 2, 3, 4 up towards infinity, then there exists a positive integer n, and notice the then, it's an if-then statement, such that na is greater than equal to b. And you can look at examples of this. Say a equals 7 and b equals 100. A and b are both positive integers. Right now, a is definitely not greater than b, but there is an integer out there, a positive integer, that I can multiply 7 by to make it greater than 100. In fact, I could just multiply it by b. So I could say, let n equal 100. There are actually lots of numbers I could choose for n. So I would say that 100 times 7 is definitely greater than or equal to 100. And that shows the Archimedean property. And it may not seem like a lot now, but it's actually used later. So here is, an example of that, and we have our if-then. Now they show this proof by contradiction, and I'm not going to go through every part of it, but I wanted to give you the gist. So since it's contradiction, and it starts with that if a and b are positive integers, then there exists a positive integer n such that na is greater than or equal to b. What they start with, they say, basically, let's suppose that our then is false. So they suppose that na is actually less than b for every. And that's an important note. You have there exists, the opposite of that is for every. So for this, there exists, there only has to be one. So if you're going to contradict, you're saying, yeah, it's not true for any of them. So you say for every. So suppose na is less than b for every positive integer. And they go from there. So they're starting with a false then, and what they're hoping to do is show that you end up with a false a, basically. So they're looking for something to go wrong in the proof. If the proof doesn't go wrong and you can't get back to what you started, there's some mistake that's made or some statement in there that has to be false, you're done. You've proved it by contradiction. So what they do after they do this is they actually say, well, you know what, let's look at one element in this, and they say we're going to start with the least element. So they say the smallest in the set of all the integers like this would be b minus ma. And you might wonder, how do they go from this to this? Well, they're not going to use this one. This is just the form. Na is less than b. If I actually look at this, I say, okay, na is less than b, and I'm going to subtract an na from both sides. So I've got 0 is less than b minus na. And this is the same form as this. So they're saying here's this number over here. Okay? Now they're not using the n because that's your general thing. So they're saying here's this one. This one fits the same pattern, but this one we're going to say is the smallest, which comes from the well-ordering principle, saying that if you have a set of things that are integers, you will have a least element. So they're saying this is the least element. It's in that set. They've done nothing wrong yet. So from here, what they did is they said, well, you know what? This b minus m plus 1a, m plus 1 times a, is also in the same set. But this one is the smallest. So what they go through and do is actually prove that this one is less than that one, which creates another false. So they have a false then statement leading to a mistake, basically a false statement. It doesn't work, and we have it failing. And that is how they conclude their proof by contradiction.